Now we're going to talk about fatty acids. We're going to break down the lipids we learned in the first section and talk about them more explicitly. Fatty acids, as I said before, consist of carboxylic acids. Even though the carboxylic acid with the N that tends to be polar, because there's so many carbons here, 12 to 18 carbons, is making it nonpolar, which is making it not dissolve in water. Because it's nonpolar as a result of the 12 to 18 carbons. They can exist as both saturated and unsaturated, and that greatly influences the physical characteristics. You may remember from previous sections, saturated means that they have all single bonds. Notice that none of the bonds here, except for the double bonded oxygen, that doesn't count, all the rest of them are all single bonds. Whereas monounsaturated has one double bond, and polyunsaturated has more than one double bond. And here's the double bond here. Take a minute to look at this double bond. Notice that on each side, the carbons are coming down. You may remember from previous chapters, this is a cis arrangement. The fact that it's cis is going to greatly influence the physical properties. And the cis arrangement is what's typically found in nature. Saturated fats, meaning ones with all single bonds, tend to pack really close together. Notice how the shape is zigzag? Because of that, they can kind of insert each other and stack on top of one another. Think of it as a can of Pringles. If you turn a can of Pringles upside down and lift up the top, you'll notice that it stacks up very neat and nicely. That's because all the chips have the same shape. Because of that, the interactions between the chains are very high, which is actually making it having a high melting point, which means it's going to be solid at room temperature. So these are things like animal fat. So if we look at this steak up here, this fat right there is caused by a saturated fat. Notice the carbon chains are able to stack nice and neatly on top of each other. Because of that, it's making it more rigid. Since it's more rigid, it's making it a solid because of the interactions. They kind of get stuck. A cis formation, however, an unsaturated cis, notice once again, here's the double bond. It's going down on both sides. It's going to the right on both sides. That means it's cis. It causes kinks in the chain. So that means that they can't stack up as neatly and nicely as the saturated ones could. Which means that these chains cannot interact nearly as well as the saturated hydrocarbons. Which is giving it a very low melting point. Because of the low melting point, it's a liquid at room temperature. An example of this would be something like olive oil or corn oil, something along those lines, vegetable oils in general. Notice they're all cis. In nature, you will typically find a cis arrangement. If we look at them side by side, here's the saturated, here's the unsaturated. Notice this is a solid, while the unsaturated is a liquid. Notice the difference in stacking, whereas this one has no interaction between them. Now, I keep saying the cis, and to look at the fact that it's a cis arrangement. If it's a trans arrangement, look at the physical shape of it. The zigzag. Notice that this one's going down and this one's going up. That means it's trans. As a result, it has the same physical shape as a saturated hydrocarbon. Therefore, it can stack like a saturated hydrocarbon can. This is not typically found in nature. This would be man-made. So when you see hydrogenated oils, or if you see something that says trans fats when you're in the grocery store for margarine or something along those lines, it's really referring to a man-made product of this reaction. And our bodies read this as if it's a saturated hydrocarbon because of the fact that it looks almost identical. So let's take a look at some examples. Notice as the number of carbons increase, the melting point increases. Here's the animal fat. Its melting point is 69 degrees Celsius. If we look at the differences between saturated and unsaturated, here's 18 carbons for animal fat. It's saturated. It has a temperature of 69 degrees for a melting point. Here's 18 carbons for a monounsaturated. So one double bond drops the melting point from 69 to 13. By having multiple unsaturated, multiple double bonds, a polyunsaturated, for the same amount of carbons, it drops from 13 to negative 17 degrees Celsius to melt. Once again, notice as the number of carbons increase, the boiling point increases. So if we wanted to compare, we want to say which one's negative 17, which one's 13, which one's 69. Notice they're all 18 carbons, so we don't have to worry about how many carbons there are. What we do have to look at is whether it's saturated or unsaturated. Saturated is going to take the highest temperature to go from a solid to a liquid. That's 69 degrees. The double unsaturated is going to melt first. That's negative 17 degrees. And then that means that the one double bond, 13 degrees. We're going to switch gears a little bit and talk about how these react in our body. Prostaglandins are a hormone-like structure, that has 20 carbons. Icosanoids is what they're also named for, and that's because ico means 20. They start with an acid that's found naturally in our cells, arachidonic acid. This is a polyunsaturated acid that then, when it starts to react, it goes from, here's the arachidonic, it closes in to the 5-member ring, and that produces an inflammation or a pain in the area. So for instance, if you hit your thumb with a hammer, that arachidonic acid turns over to the prostaglandin. The only difference between the two of them is that 5-ring carbon, the substituents on that 5-ring carbon. So if we go back up here, here's the 5-ring carbon. Here's the substituents on the 9th carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9. They started counting at the carboxylic acid. That's where they got the 9th carbon from. Notice one's an OH and one's a double bonded oxygen. That's the only difference between the two. They have many functions like affecting the blood pressure or contracting and relaxing of uterine smooth muscles, or they could also increase inflammation. If we take NSAIDs, which stands for non-steroidal anti-inflammatory drugs, they block the production of the prostaglandins, which means that you're not going to get that pain, you're not going to get the inflammation. So an NSAID would be something like an aspirin or ibuprofen. We're moving on to omega-3s and omega-6. You've heard, no doubt, a lot about omega-3s in health recently. That's because they are noted to be healthier. They're better for our cholesterol levels and things along those lines. When we're talking about the omega-6, we're talking about things like olive oil. And you may have heard of news-related articles that talks about this. The omega-6 means that the first double bond is on the 6th carbon. Omega-3, the first double bond is on the 3rd carbon. So for instance, here's 1 carbon here. This is times 4, so there's 4 more. Here's the 6th carbon. And then here's the omega-3. 1, 2 on the 3rd carbon is the double bond. Remember, the double bonds are cis, which means that it's going to interrupt the stacking, which means that they're going to be liquids at room temperature. And that is it for fatty acids.